Hello friends, today we'll show a simple assembly and structural analysis of a table using SolidWorks. The model is consisting of 5 different parts. It has already been modeled using SolidWorks. Let's start assembly. Let's select the models from here itself. It is consisting of stand, base leg, top plate, top support, and finally top support 2. We have taken all the 5 different parts together. This is the leg, this is the central support, top plate, top support 1, and this is top support 2. 5 different parts are there, right? First of all, we have taken this one. As per rules, it should be fixed, so we have to make it floating. And this central support should be fixed, so we can make it fixed, right? These are all different parts. Okay, now we can start our assembly. First of all, we have to put that base support at this location, right? So we can start from assembly itself, starting with met. First of all, we have to select that location for mating, so we can make this model bigger for better selection of specific locations. Met, this location should be met with this place. One constraint is done. We have to follow 2 different constraints also. Then the second constraint is this plane should be meeting with this plane. Green check. And the last constraint is remaining. Last constraint is the meeting surfaces should be selected. So we can make it a little bigger for better selection. That means this face should be meeting with this face. All the 3 constraints are satisfied. So green check, it is done, right? You can see clearly first constraint, the first leg is already made. Okay, done. Now at 2 more different locations we have to assemble this leg. We can do it using circular component pattern. So circular component pattern, direction to be selected. With respect to this central axis, we have to provide this leg with an angle of 120 degree. We want to provide 3 different legs, right? One is already provided, 2 more are needed. 120 degree, and numbers should be 3, including the original one. Next, it is asking components to be patterned, so we have to select that component. This is the component. Green check, it is done. You can see 3 legs have been assembled. Next one, at this location you have to provide this top support. This one to be provided here itself, right? Okay. So what to be done is, in this case we can do the axis of these 2 different objects should be met together. That is front plane of this one and front plane. Right plane of this one should be meeting with right plane of this one, and finally this surface should be meeting with the base bottom of this one. So starting with met, we can select the part separately. Stand, or let's select the front plane of this base support should be meeting with front plane of this one, right? Both the planes are met. Green check. Now the right plane of this one should be meeting with right plane of this support. Right plane of this support should be met. Done. 2 constraints are satisfied. Green check. Now the last constraint, that is the mating faces, right? We can make it a little bigger for better selection. So this face should be meeting with the bottom face of that one. Let's make it a little bigger for better selection. Green check, done. All the three constraints are satisfied, so it is made. Perfect, right? Next one, the other top support is also remaining, that to be assembled here, this part, right? So we can bring it a little close to this one, right? Now start mating, starting with mate. This edge should be meeting with this edge. One constraint is done. We can drag it here. Again, the bottom face of this one should be meeting with the bottom face of this one. Again, two constraints are met. The last one, that means this face should be meeting with this face. All the three constraints are satisfied. Green check, it is done, right? Can make it a little bigger for better viewing. Done. Next, what can you do is, this part we can use as a mirror component. So starting with mirror components, is asking about the mirror planes. So we have to select this plane as the mirror plane. So what can you do is, we can select that plane of this base support, front plane of the base support as the mirror plane. Now components to mirror, we have to select that component. Green check, it is done, right? Okay, now the last one, that is the top plate should be met at the surface. Here also in this case we want three different constraints to be satisfied. We're starting with met. First of all, the bottom face of this one should be meeting with top of this one, right? So we can make it a little bigger for better selection. One constraint is met. Two more constraints are needed, right? So what we'll do is, with respect to the base support, we have to select the different planes of this one. The front plane and side plane of this one should be meeting with front plane and side plane of that one. Okay, so we're selecting the front plane of the base support should be meeting with front plane of the top support. The top plate front plane is required. Green check, two constraints are satisfied. The last one is required. Now you can see the right plane of the top plate should be meeting with right plane of the base support. Green check, all the constraints are satisfied, so it is done. Now you can see it is fixed, it is not rotating. So this is our assembly. Green check. For better viewing, we can change the background, plain white, it will be better for viewing. This is our assembled model. Next one, we have to go for analysis. So for analysis, we are starting with simulation. It is a new study and we are going for static structural analysis. Green check. First of all, we have to provide material to all these different parts. Apply material to all. Let us select ASTM A36 tail to all the materials. which is having modulus of elasticity 2E5, 2 into 10 to the 5 Newton per millimeter square, and Poisson's ratio 0.26. Apply, close. Material is provided. Next one, we have to fix it. We have to fix the base support. So fixture, fixed geometry. The base should be fixed. We can fix the base here itself. Green check. So it is fixed, but it is not perfect because this one has a tendency to rotate also. That should be restrained, right? So we can apply some other advanced fixtures. This is a cylindrical face, so we can select the cylindrical face, and that should be restrained with rotation. It should not rotate. So we have provided zero rotation of that one. By the same time, we can provide zero displacement of that support. Green check. So it is fixed. Now we cannot rotate. Next one, we have to apply load. External load, we have to apply pressure. And the unit you want, megapascal, that is Newton per millimeter square. Let us provide 0.1 megapascal pressure we are applying on that tabletop. Green check. So pressure is applied. Now we can mesh and run. You can see the results. Yield strength is 2.5 10 to the 8 Newton per meter square, whereas the maximum stress developed is 9.96 10 to the 7. So our model is safe, right? You see the factor of safety in this case also, it is 2.5 into 10 to the 8 divided by 9.9 10 to the 7. It is safe, but we can find out from here also. Now the thing is, you can see in this case, this is the model is safe, but we have very much high stress at this bottom supports. For better designing, what can we do is, we can change these things again. Now we have to see the maximum stress at which location. You can see it from here also. Edit definition. First of all, we'll see these things in the form of Newton per millimeter square, and here excessive deformation it is showing. Now we can change it to true scale. Now we see, now you can see here the deformation is not that much, right? It is as per true scale. Though the stress value it is maintaining very nicely, that is, it is below the yield stress, it is safe, but at this location we are having high stress. Let us see the stress values with probe. At different location we can see different stresses. Here in this case, stress value is 4.01 10 to the power 1, that is 40 megapascal. This one is also safe. Here you can see in this location is also 71 megapascal, right? So at different location you can see at top surface here it is very less, it is 52 megapascal, whereas the yield stress is 250 megapascal, right? In this way we can see the stress values at different locations. Now we want to see one thing, like factor of safety, how much it is. We can check it from here, new plot, factor of safety, green check. Here you can see factor of safety is very high. Minimum is 2.5 and maximum is 1 into 10 to the power 16. That means it is a wastage of material. 2.5 is also okay. So we can design these things in such a way that factor of safety is 1 into 10⁶, that can be reduced. Parts which one is having maximum load is this one only, right? And the base legs are not having that much of stress. Stress value at this support is very less. What can you do is, for designing these things, we can minimize the utilization of material in this case, right? So this is all about our today's assembly and analysis of a mechanical component. This is a very simple analysis.